Subtract 1, then divide by 2.
To retrace a journey, you have to swap your starting and ending points and walk every step in reverse. The same logic applies to algebraic equations. Here, the function maps an input x to 2x plus 1. To reverse that rule, we start with the output of the function. First, we undo the addition by subtracting 1. Then, we undo the multiplication by dividing by 2. Working backward through the sequence gives us the exact return path. Subtract 1, then divide by 2. This logic of reversing inputs and outputs also applies directly to individual coordinates along the path. Finding the inverse requires us to swap the x and y values entirely. The original output becomes the new input, and the original input becomes the new output. Reverse the coordinates, and you find the new location. The inverse contains the pair 13, 4. If every single point swaps its coordinates, where will the reversed path appear on a graph? We can plot our original coordinates right here on the water's surface, using this diagonal line to represent y equals x. When we map a point like AB,
in a separate relation, 4, 13 reverses to 13, 4.
To its new position at BA, the geometry folds directly across that center diagonal. The inverse graph is a mirror image of the original. They reflect across y equals x because inverse points swap coordinates. Reversing the pairs gives us the inverse relation. But there is one final check. We have to decide if this return path is actually a valid function. Look at this section of the original path. The inputs 1 and 2 both lead to the exact same destination, an output of 5. If we imagine reversing those pairs, the input 5 now attempts to point back to two different outputs, 1 and 2. A valid function can never map a single input to multiple outputs. So can this inverse relation be a function? No. Its inverse would not be a function because one output is repeated in the original function. Whether we are undoing algebraic operations, swapping coordinate pairs, checking lines of reflection, or testing output paths, the structure remains consistent. The environment shows the relationship, and the notation records it. Which mark in the environment proves the mathematical relationship, and how does the animal action make it true?
Swapping coordinates reflects points across y equals x.